have discussed with Lorena how we do the exam, and we discussed that we do oral exams. I'm not sure how many wants to do it.
One question maybe.
Yeah.
Will you be doing the exams or will it be Nia?
It will be me, yes.
Okay.
Me and Lorena. But when Dieter wants to join, then he can also join. I will let him know.
All right.
Yeah. All right, good. Then let's keep going. Okay. I hope you see that. Okay, last time we started with organic semiconductors. Yeah, I already started with that. And yeah, I would quickly like to go very briefly through the physical properties of organic semiconductors. So mostly conjugated polymers, why are they semiconducting? And then hopefully today I can also introduce organic solar cells. Okay, these slides I have shown you already. Yeah, these are examples of p-conjugated carbohydrates. So organic molecules have always carbon and hydrogen. And the semiconducting properties come from the p conjugation, which I will explain in detail what this is about. Yeah, they have very vastly different optical properties depending on the band gap, and an infinite amount of molecules can be chemically synthesized by changing the chromophores, the repeating units, and so on. This is one example of a series of molecules with very different absorption properties. Yeah. The Nobel Prize was given in the year 2000 to these three gentlemen, among them Eager, who is very well known in the research area of organic photovoltaics as well. And yeah, this was an interesting comparison between the conductivity of conjugated polymers. Okay. Conjugated polymers and other materials. So the conductivity, it is not only a semiconducting material, but it can be also highly conductive. For example, P.PSS, if you dope it, then you can reach conductivities comparable to metals as well. But they can be surely also very insulating. Yeah, so it's a very broad range of conductivities. Depending on the repeating unit and the length of the conjugation, so how long the pi orbitals extend over the molecule, the lower will be the band gap. This I will explain later. This is just an example of materials with very different, some molecules with very different band gap, ranging from 1 to 3. Yeah. Often these are thiophenes, for example. I don't know much about all these chemical names, to be honest. That should be a thiophene, also present in P3HT. Okay, this shows just some examples of conjugated polymers. They can be very flexible and they can be tuned in different colors. So the application ranges from photovoltaic windows, for example, to illumination and displays. Of course, where OLEDs have completely revolutionized the market, as you know. So flexible electronics can be made with this. And yeah, here's an example of organic solar cells on a bus stop. Yeah, looks also nice. All right. What about organic solar cells? So they were stuck for a long time before the introduction of non-fullerene acceptors. So when I was researching on organic solar cells, the acceptor unit was always a fullerene, which is like C60 with a polymer chain attached, for example, or a fullerene as acceptor. So there's always a donor and acceptor, and it's blended together to form a bulk heterojunction. So it's a fine network on the nanometer scale. This I will discuss in the next chapter more. But since 2016 or so, approximately non-fullerene acceptors have been introduced. For example, this Y6. And this is now the working horse for all efficient organic solar cells. Yeah, so I think most of the recent records use this Y6 as a non-fullerene acceptor. Yeah, and you see here, probably this is the record cell at the moment. The efficiencies have been going steeply up, but now they seem to saturate again. So this combination, this bulk heterojunction of D18 and Y6 gave an efficiency of over 18%. And notice the JC is even higher than in perovskites. So you can reach over 27 milliamps. There are not many combinations available with even lower band gaps. I think there are some which reach around 30 milliamp per square centimeter, even lower gap organic solar cells, but then they have more voltage losses, and yeah, this is among the optimum band gap range at the moment. The band gap is usually around 1.4 now at the moment, so it's quite it's in an optimum regime of the Shockley-Quasar model. So yeah, notice the low band gap here, depending how you see it. Compared to silicon, it's of course a high band gap. Compared to perovskites, it's a quite low band gap, except for thin perovskites. All right. So yeah, as you know, the advantage of organic solar cells is also the wide range of processability, and so they can be made from solution deposition, from vacuum, not from vacuum, but from roll-to-roll printing, from spin coating, as we do usually in the lab. So yeah, as most of you know, a solution is mixed together, and then, like shown here, like illustrated here, a drop of the material in solution is put on a transparent conductive oxide, and a film is produced by spin coating, and that leads to a rapid evaporation of the solvent, this fast spinning, and the film crystallizes. Yeah, this is quite standard. And this solution processability always is promising for industrial applications, because you can do large area processing, ideally roll-to-roll processing. Here are two methods are shown: general roll-to-roll pressing, where there are literally rolls and a film is tracked by 1 volt as shown here, and there's kind of like an opening where the material is put onto the film, and then you can imagine how it works. Like printing a newspaper, this would be another possibility where there are multiple rolls. It's called gray view printing, where the material is put onto the film that rotates around onto the foil. So this can be also applied to foils, flexible foils, because we have no high temperature processing. So you can make flexible large foils, and they are coated from a solution, in a solution bath. Basically, it could be brought onto the material as illustrated here, and this can be very fast, and you could make very large areas with this. For example, up between 1 to 100 meters per minute. So, in generally, these processing methods are very cheap, and they have been always the dream of the third generation photovoltaics, that you can roll to roll process them in large sheets. However, this has not made such breakthroughs yet, because it's always very difficult to make perfect solar cells. These large, there will be always inhomogeneities. There's a problem with the sheet resistance. So I'm not sure about the record efficiencies for roll-to-roll fabricated films, but they have not yet made a noticeable breakthrough at the moment. So industry that really wants to sell third generation photovoltaics like perovskites or organic solar cells, they often go back to evaporation. So we will see if that will ever become the reality in the industry. Okay. Okay, so what about the electronic structure? So we are discussing the questions, why are organic semiconductors semiconducting? And this is all about the arrangement of the molecular orbitals. So let's discuss molecular orbitals. You see here, a hydrogen molecule, and the hydrogen atoms, they have their s orbitals, right? First shell, and they have 1 electron. If you bring these 2 s shells together, like so, then a molecular orbital will be formed, which is now called the sigma bond in this case. So generally, we can say that the overlapping of atomic orbitals leads to molecular orbitals. And they can have bonding or anti-bonding properties. So if you bring 2 molecular orbitals together, 2 atomic orbitals together, like so, then you will also form 2 molecular orbitals, and one will be bonding and one will be anti-bonding. The anti-bonding in this case, so this would be the bonding. The anti-bonding would look like this, I think. It would be repelling the 2 s orbitals from each other. And so typically Yeah, so the most basic molecular orbital is the sigma bond. Molecular orbital, you can say. And a sigma bond does not need to be necessarily formed by s orbitals, but it can be also formed by the SS orbitals, by sp, and even pp orbitals, and hybrids of those. So the next atomic orbital shell after the s is the p, right? Okay, we will see how this works for more complicated bonds. And yeah, so let's have a look at carbon-based molecules. For example, diamond, graphite, or fullerene. All of these three crystals, or all of these three materials, are only formed by carbon atoms, right? And a carbon atom has 4 valence electrons in its shell. In particular, as we discussed already, it has 2 filled. The s orbital is filled with 2 electrons, and there are 2 more electrons in the p orbitals. So this we have already shown in the last slide, the s orbital, and then there are at least 3 p orbitals in x, y, and z direction. By the way, what are these? What is this exactly? Like this? I don't know how we would call it, like a weight or like a hantel. So what is this exactly? Well, that's the probability. That's the distribution probability of the electron. So the electron is delocalized within this area. So the electron can be in this physical space. This is what these orbitals are showing here. And so what happens, how a material or a semiconductor, for example, or a certain crystal is always formed, it is all based on the hybridization of atomic orbitals. So when carbon atoms, for example, are brought together, or silicon atoms, first the hybridization of the atomic orbitals will take place. What does that mean? It means, as shown here, that the atomic orbitals, they morph together into equivalent atomic orbitals. So if in the example of carbon, these 2s and the 2p orbitals, they go into such 4 sp3 hybridized orbitals, then we speak about a sp3 hybridization. Yeah. But there are also other types of hybridizations which are shown here. So if atoms hybridize in sp3, so the atomic orbitals morph together and form new hybridized atomic orbitals. If you bring sp3 hybridized atomic orbitals together, you form single bonded carbon hydrides, such as ethane. Yeah. And this is actually not conducting. So this is an insulator. Yeah. So the reason why this is not conducting is that all the electrons that are available, they are bond, basically. They're bond and they are stuck with their atoms. So all the electrons that are available, they only contribute to holding the molecule together, simply speaking. So this is completely insulating. Although this also forms polymers, yeah, but non-conjugated polymers. Non-conjugated. And this is often plastic, for example. Yeah, all the polymers that are not semiconductor. Yeah, so this is actually the vast majority of carbohydrates. And molecules that exist, I guess, on average. Okay, but what if there is a sp2 hybridization? So now there are two of these there are two of these or three of these sp3, a bit confusing. So there are three of these sp3. This one, let's say, and this one. And in addition, there is one PZ. There's one PZ molecular orbital. These are those ones. So this is called PZ. And sorry, this is still a. If you speak about one atom, we are talking about atomic orbitals. If you speak about the molecules, we are talking about molecular orbitals. So if you have a hybridization like this, there are still three of these yellow ones available and one PZ, atomic orbital. Now, in this configuration, so-called pi bonds can be formed when you bring two carbon atoms together, such as the example of ethylene or ethene. And this is a conjugated. This forms a conjugated polymer. So that's very important because this is semiconducting. Yeah, sorry, writing is not really nice yet. I think you know what I mean. Semiconducting. So why is it semiconducting? Generally, the semiconducting properties are due to delocalized pi molecular orbitals. So you have these pi molecular orbitals, and these are basically additional molecular orbitals where the electrons can move around. While there is still a sigma bond here available that holds the molecule together, simply speaking. Right? So there are now states available that can conduct charges more easily. And there's another example where you have now two pz orbitals or two p orbitals and two sp3, and then this is called sp hybridization. And this forms actually a triple bond. And then you have two pi orbitals like so. And this molecule is called acetylene or ethene. And this should have a triple bond. And this would be also semiconducting, I think.
Sorry, Martin, can I ask something? So for the double bond, I've forgotten a bit. So are you saying that the double bond is formed somehow as a mixture of the sigma and the pi bond?
Yes.
But shouldn't there be a double bond between the two carbon atoms, namely where you have marked the sigma bond? So when two carbons would connect with a double bond between and then have two single bonds on the sides, resulting in a four-valence element? Because if you just have there the sigma bond between the two carbon atoms, that's like a single bond, and then I don't understand what's the p bond popping up. If I'm explaining clearly, maybe it sounds stupid.
Yeah, but there should be now a double bond, in my understanding. Should be like that, huh?
Yeah, exactly. But that's a double bond. But then that's the double bond that you drew. That should be the orange region on the figure on the right, where you have marked a sigma bond, which is a single bond. So then somehow the double bond is a combination of the sigma and the pi bond, but somehow the pi bond is popping up, and between the carbons it seems like there is no double bond.
In my understanding, the double bond consists of the pi and the sigma. But
and it is between the two carbon atoms somehow.
Yeah.
Okay. That means nothing bonds anymore, of course, because everything is bonded as it should be.
Yeah. Yeah, everything is in bond in this case. But, I mean, when you bring more carbons together, then there will be alternating double and single bonds, and then this double and single bond can move around. This is like how the conduction.
Yeah, that's clear. Yeah. What confuses me is basically how the double bond forms from the sigma and the pi bond, and how on the 3D graphic, or kind of 3D graphic, it looks like there is a single bond between the two carbon atoms, the sigma bond, when it should be a double bond. So the figure implies that the double bond is made out of the sigma and the pi bond.
Yeah.
But I can't imagine this, how it is. Maybe like my organic chemistry has been a bit rusty for the past year or so.
Yeah, I understand your problem, but the pi bond, there is also bonding. It is also two states, right? So this is maybe shown in the next slide. Yeah, it's like that. So this is the ethylene again. The pi bond, which we have shown above in 3-dimensional, it has also a bonding and anti-bonding configuration. And in ground state, this would be occupied, and yeah. And contributing to the bonding, in my point of view. So maybe you can. So do you think that this is correct? That this is correct, the chemical formula?
Yeah, that's for sure correct. Yeah, absolutely no doubt about that for the double bond. But judging, like what I was saying, is that when you think about this scheme, and when you look at the 3D kind of figure with orange and purple, then from here you can conclude that the sigma and the pi bond together make the double bond. Yeah, so I think the next slide was a little bit more explaining a bit better how this would look like a double bond. Yeah, so I have forgotten this a bit, so I was just wondering how it happens with the orbitals, how they overlap to make the double bond, and yeah, here I think it's better explained.
Yeah, all right, yeah, thank you.
Sorry, maybe for the others this was a bit of waste of time, but I did this like in first year at university chemistry, and it's been a long time since then.
Yeah, just let me know if I'm talking nonsense. It could easily be. My knowledge is also a bit rusty. Yeah, so if something does not make sense, just cry out. And all right, good. Then let's go on. So, in my understanding, the pi bond would contribute to the bonding if it's occupied here. So this again, you see the atomic orbitals, and then they form together, forming these molecular orbitals. So in this case, yeah, we bring two atomic orbitals together on this side, and two atomic orbitals together, and they split into four molecular orbitals, as shown here. And the p set split into bonding pi orbitals and anti-bonding pi orbitals, such as the sigma bonds split into bonding bonds and anti-bonding bonds. So now in the ground state, the pi orbital, it would be bounding, so like this sort of, and it would help also contribute to the bond, and it would form a double bond with the sigma, as discussed. However, it can easily be excited, and then the pi orbital could go into the excited state. But this we will talk later. Okay. Okay, what else do you see here? So also here you can see the sigma and the pi bond. And here's again a 3D representation. And yeah, here the summary again. The sigma bond forms some overlapping sp2 hybrid orbitals. And the weaker pi bond, why is it weaker? Because this energy is not so far down. It's not so strongly holding the molecule together. And it can be also more easily excited. So this double bond can break. The weaker pi bond forms from the pz orbitals, as we discussed just before. And now we see that the pi and the pi star form the HOMO, the highest occupied molecular orbital, and the lowest unoccupied molecular orbital. So these are the most important terms for organic semiconductor in terms of the energy levels that define the optical properties, the HOMO and the LUMO. Okay, and yeah, the whole molecular backbone is held generally together by sigma bonds, and the electronic transitions and conduction happens between pi and pi star molecular orbitals. All right, what do we have here? Yeah, this is again a three-dimensional view of the atomic orbitals and the top view. And yeah, maybe comes back to the question how the bonds look like. In the ethylene case, sigma bonds formed by a combination of sp2 orbitals along the connection axis, as shown here. And yeah, this we have just discussed. And the pi orbitals form from the pz orbitals, as shown here. Yeah. And yeah, that's the chemical structure indeed. And okay, so how do the molecular orbitals look like in the ground and the excited state? So again, let's only focus on the p orbitals. So only on those ones here in the case of the ethylene. So there are p orbitals, and this is two p orbitals, right? We bring together from two carbon atoms. This is one carbon, and this is the other carbon. And then pi bonds, molecular bonds are formed. And how do the individual atomic orbitals form? Well, there is a sort of pi aligns like this. So the pi is kind of in phase, as shown here. And so where the positive probability of occupation is upwards, and that is from this is the representation of the pi molecular orbital, and the pi star orbital forms by a destructive overlap of these two p orbitals, right? So they are kind of asymmetric. And this is then the antibonding pi star orbital. So the molecular antibonding pi orbital would be a destructive overlap, and it would be asymmetric, as shown here. This is the pi star. This is the pi. Okay. And yeah, typically this one is occupied. So it's occupied by two electrons in the ground state. And this is unoccupied. But it exists. And it can be easily excited into. And this actually means this is occupied by a spin up and spin down electron. So this molecular orbital can be occupied by, it is occupied by two electrons from both carbon atoms. They contribute one into this molecular bond, right? Okay. So let's discuss higher lying states. So how do they look like? Again, in the ethylene case, we have just shown here that the p molecular orbitals look like this, p and the p star. So now a larger molecule, the butadiene, as shown here. So actually, so this sp2 hybridized carbons, they lead actually to an alternating double and single bond if you bring more carbons together. Yeah, so semiconducting polymers, you can also say, why are they semiconducting? Because of the existence of alternating double and single bonds. This double bond can be passed along kind of the chain in a simple picture. Okay, so now we look at the butadiene, which has 4 carbons. So we bring together 4 of these pi z orbitals. and we look how the molecular orbitals look like. So there are always sigma bonds, right? Forming one part of the bond, but now we just look at the p bonds, p atomic orbitals that form the sigma, the pi molecular orbitals. So there are multiple symmetric and asymmetric combinations. So those two have the lowest energy. They are symmetric, and these are asymmetric in a way, and they have higher energies. So this one is the most symmetric, and then this one is the most asymmetric, or the most destructive overlap. All right. And therefore, it has the highest energy. And then again, those two would be occupied, and those would be on top here, all unoccupied. Okay. So these pi orbitals could be described as eigenfrequencies of the molecule. So you can see these molecular orbitals as certain vibration frequencies, and the higher the energy, the higher the frequency, as shown here. So these are like the eigenstates of this molecule, basically. And yeah, this is even more complicated. This is now a hexatriene, so with 6 carbons. And then again, there are symmetric pi orbitals and asymmetric pi orbitals. Yeah. So does anyone know? So they are not all asymmetric, obviously, on the top. It's also asymmetric, symmetric, asymmetric, and here symmetric. What's it doing? It just crashed. Okay, I need to open again. Completely crashed. Okay, almost there. Sharing again. And opening again. Okay. Yeah, welcome back. Okay. So the antibonding molecular orbitals, in case of this hexatriene, they are not always asymmetric. As you see, asymmetric, symmetric, asymmetric. Again, here, symmetric, asymmetric, symmetric. Nevertheless, this has a higher energy than this one. Or, yeah. So does anyone know the answer? Why this one has a higher energy than any of those at the bottom? Yeah. Something to think about if no one knows that. All right. So, interestingly, you can even measure directly these molecular orbitals, which is shown in this slide. You can measure it with a scanning transmission microscope, with a STM, which has a very high resolution. Scanning tunneling microscope, I guess, in a constant current mode. So in this work, which was published in Science, they have measured single molecules on such a copper natrium chloride substrate, as shown here. So you can visualize single molecules, which is pretty amazing. So they saw here 6 single molecules. And if you look at this here, they can actually measure the HOMO and the LUMO. So this was in case of pentacene. This is one of the most famous organic semiconductor molecules. So remember, the HOMO and LUMO are pi orbitals, pi star and pi. And yeah, so depending how much voltage they apply, probably they can measure the electronic distribution over the whole molecule. So this is like a drawing from the actual image. So this illustrates you that like a molecular pi orbital is delocalized over the whole molecule. So it is occupied by 1 or 2 electrons, depending on the configuration. But it exists. There's an occupation probability across the whole molecule. So this is when we're talking about delocalized electrons. And the LUMO in this case looks like this. Yeah. So this is pretty interesting. Do you have any questions so far on this part? Okay, then we go on with the electronic properties of organic semiconductors. So that is another important feature of organic semiconductors. And this says, so this slide is about showing you that the longer the conjugation, the lower the band gap. So here the repeating unit in this PPB molecule was increased. So note here the axis here is 1 over the repeating unit. So if that value is 0.1, then the repeating unit n is 10. And here, this would be infinite repeating numbers. And this here would be the repeating number, it's 5. And for this repeating number of 5, the band gap is high. And yeah, this is these molecules in different conditions, like vacuum solution doesn't matter so much. But for all states, the longer, excuse me, for all states, the longer the repeating unit, the lower the band gap. So I'm pretty sure you know why this is the case. Does anyone want to say that? If not, yeah, remember when we discussed the formation of the band structure. So n number of atomic orbitals split into n molecular orbitals. And so if you bring more and more together, all of these molecular orbitals need to have different energy, right? Because they cannot exhibit like this electrons and fermions, and they cannot exhibit the exact same quantum state. So therefore, the molecular orbitals need to split more and more. And if you bring more and more pi orbitals together, the molecular orbitals need to split more and more, and the band gap will shrink. And this is described by this formula, actually. So this is also taught in polymer science. I guess some of you have heard that, for example, Shu last year. Yeah. Okay, and this does not go to infinitely low band gap, which is due to Payot's theorem. So the band gap does not go to 0. E does not with repeating with infinite repeating numbers like here, because at some point the molecule will twist so strongly and so on, so that they are not talking to each other anymore, all these different molecular orbitals. Yeah. So there will be a finite band gap at the end. But in principle, the more pi orbitals you bring together, the lower the band gap. So you want to increase the conjugation length and lower the band gap, if you want. And yeah, this shows a graph for this PPB molecule with different repeating units. So 1, 2, 3, 4 repeating units. And it shows the absorbance and the fluorescence of that molecule. And yeah, more repeating units, the higher the absorption coefficient. So the absorption will be here, and the emission is kind of mirrored, which has lots of reasons. Not sure if we should go to this today. Yeah. So there is a relation between the absorption and the emission, as you know, and this depends a lot on the molecule, on the environment, and so on. Okay, so this was again the formation of the band gaps. If you bring two molecular orbitals together, it looks like that. That's actually two together from each side. Then we have this molecular orbitals. If we bring n molecular atomic orbitals together, we get n molecular orbitals, and they form very finely split molecular orbitals and occupied states, and they also form unoccupied states and unoccupied states, as you see here. And yeah, this gives then rise to the conduction and the valence band, or the HOMO and the LUMO. Okay, there's another chapter on charges and excitons. Okay, so we have half an hour left, and since next time will be the last lecture, I need to cut this chapter quite a lot, or the following. I can go quickly through the remaining slides here, and then I quickly want to introduce organic solar cells. So this shows you a slide of states and configurations in organic semiconductors, in principle, especially polar ones, singlet states, and excited states. So why is this important? Well, there's one important thing in organic semiconductors. When the molecule is excited, because there's such a strong interaction between the electrons, because the dielectric constant is low, so any excited state will cause a massive disruption to the molecular configuration. So the molecules will rearrange when there is an extra electron added to the system, for example. So why is this important? Yeah, so in organics, we speak about not free electrons and free holes, but we speak about free polarons moving. So the polaron already considers the distortion of the lattice due to the charge. So the position of atomic cores will be redistributed to reduce the energy of the new state when you add an electron. And the polaron can be understood as the coupling between the state and the geometric electronic configuration. So when a charge moves, basically it carries around with it a large distortion of the lattice. This is very particular to organic semiconductors. So we don't speak about free electrons and holes. We need to understand these moving charges more as polarons. This is the take-home message of this slide. And very important is also the charge transport in organic semiconductors. And there are two types of transport. So as we discussed before, there are these delocalized pi electrons, right, on the molecule chains. So they are delocalized, and the movement of the charges can be understood by a band transport. However, then to jump from one chain to the other, there needs to be sort of a hopping transport. And this is usually 1 million times slower than the band transport. So just to give you one number, this could be a mobility of 10 square centimeter per watt seconds, and this could be 1 e minus 5. So this hopping dominates the transport in organic semiconductors. Okay, I need to speed a little bit up to show you some organic solar cells. So remember there are two types of transport mechanisms in organic semiconductors. Band-like transport is like silicon. It is a bit slower than silicon because even that single molecule chain is not that ordered as a complete crystal structure and many other reasons. But in any case, there needs to be a hopping process. So the charge just sits there and waits for sufficient thermal energy to make one jump to the next one. So it's a thermally activated and field assisted and concentration dependent hopping mechanism. So the mobility is a function of the temperature, the electric field, and the charge carrier concentration. So if you bring many organic semiconductors together, you can understand the whole available states in that film as a distribution of states, of molecular states, energy states available, and charges need to hop between these states. And so the mobility depends on various parameters due to this hopping mechanism. In particular, with higher temperature, the mobility will go up. This is exactly the opposite of band transport. So in organic semiconductors, if the temperature is higher, there's more energy available for hopping transport, and the mobility goes up. Okay, this is a slide showing you typical mobilities in organic semiconductors for different materials, P4HD, PCDTBT, and it depends a lot how you measure it. For example, with field effect transistor measurements, there's like a horizontal movement. And in these measurements, the mobility is usually much higher than the vertical transport. This could be because molecules are better aligned on this horizontal direction. So typically time of flight or something like that. So SCLC, this measures vertical transport between the two electrodes, and this measures horizontal transport. And this mobility is much higher usually than this mobility. So one needs also always to be aware of what kind of technique there is to measure these mobilities, but they're typically very low. Okay, this goes on, discusses ground and excited states. Ground state and excited state. The excited state has a LUMO here, has a free electron in the LUMO, and the HOMO is partially emptied in the excited state. This electron would be delocalized over a whole chain, in this case in pentacene. And so after the photoexcitation, an exciton forms, and in organic semiconductors, this is super strongly bound because of the low dielectric constant. So this excited state is localized to one chain. And this is shown here. So how far this exciton extends in organics, and in semiconductors, the exciton is much larger. And in organics, the exciton is called a one-year exciton, and in organics, a Frankel exciton. Sorry. Okay. This is a slide that shows the binding energy of exciton. So this is quite interesting. If you measure on P3HD with the thiophenes in repeating unit, if you measure the band gap with UPS, not sure if you're familiar with that, but UPS allows to quantify the occupation of the molecular orbitals and to directly measure the density of states here in the valence and the conduction band or the HOMO of LUMO. So when you measure P3HD, the optical gap is 2.6 eV. However, when you measure the EQE, you can only transport charges with a band gap of around 1.9 eV. So that is typically, this does not give free charges. So this allows so you need to overcome, when you excite the P4HD, you need to overcome also the exciton binding energy to split the exciton. The exciton binding energy in this case is 0.7 eV. So this is how strongly the exciton is bound together because of the low dielectric constant. So there's always a problem to split excitons in organics. Okay, this is also quite fast, but the exciton, because the dielectric constant is low, they always feel each other. The exciton is bound by 700 millielectron volt. Remember the room temperature, the thermal voltage is 25 millivolt. This is how much fluctuation the room temperature gives you in energy. 25 millielectron volt compared to the exciton binding energy of 700 millielectron volt. So the room temperature cannot split this exciton. So the exciton will be always like bound together and move around. This slide shows you that how far excitons move, and at room temperature they can move around for 10 nanometer. They diffuse, but they're so strongly bound they don't split. So they will eventually recombine. And this is the diffusion length. And that is the diffusion length in red here. This in green is the diffusion coefficient. Doesn't matter so much. So the higher the temperature, the longer the larger they move around. This explains the reason. So if they have higher temperature, the exciton, the charges are able to maintain their energy without going to real low energy states. So higher temperature, lower temperature. And also you see this downwards relaxation at low temperatures from the PL peak. So at higher temperature, the PL peak is centered at a lower wavelength, so at a higher energy. So let's say this is wavelength, and this is the PL peak. So I'm explaining this picture and this. At low energy, the wavelength is higher. So the energy is lower because they relax down, and here at higher energy, so T is low, and here T is high. And at higher temperature, they maintain a higher energy and therefore a lower wavelength. Yeah, it's not so important. Take-home message here is mostly that they diffuse 5 to 10 nanometers, the excitons. Here is a slide that discusses the different terminology in organic and inorganic semiconductors. For example, inorganic conduction band, LUMO, valence band, and HOMO inorganics. Free electrons need to be considered as negative polymers. Holes need to be considered as positive holes. And here we have weakly bound 1 year electrons, and for organics, the Frankel excitons. Okay, so this is the summary of the organic semiconductor part. Yeah, p-conjugated polymers comprise sp2 and sp hybridized C atoms. This leads to p-conjugated molecules, pi-conjugated. This we even can measure, like with the STM measurements, that the pi orbitals are delocalized over the whole molecule. Pi-conjugated molecules are semiconducting molecules. And polymers, they have widely tunable band gaps. Electrons and holes can be understood as charges localized on individual molecules. So the charges, they remain strongly localized on one chain. And if the polymer is very long, then on one block. So this conjugation does not extend over the whole crystal. It's localized on the individual molecules. And the excitons are strongly bound, and it's called the Frankel exciton. And organic semiconductors have low charge carrier mobilities because of that hopping, but very high absorption strength. And there's a very strong coupling between the photon and the electrons. So one molecule can already absorb the photons. So as a comparison to other semiconductors, the absorption is typically very strong in organic materials, organic semiconductors. Okay, now we have 15 minutes left. Do you have any questions?
Maybe one small question. How can we decide if a molecule is hole conductive or electron conductive by the structure formula?
That's a very good question.
Or can we decide at all?
Yeah, I'm pretty sure that experts would be able to tell if it's going to be hole or electron conductive. I'm thinking if I can answer that. Yeah, you're right. So typically, conjugated polymers are either hole or electron conductive. They don't, sometimes they are ambipolar as well, but usually they conduct either holes or electrons really, really well, and the other one not. I'm trying to find an image if you see any differences. Yeah, it's a good question. I cannot really answer it, but I will write an email or put the answer on Moodle. I cannot, I don't see why.
Okay, cool.
It can be answered through the mobility of hole, either hole or maybe electron, because the transport of hopping transport dominates the charge transfer, right? So if the whole transport, hopping transport is higher in a particular polymer, we would say that's a whole conductor, and in the other way around, vice versa for electron transport polymer.
Yeah,
that's my idea. I don't.
Yeah, but why is it like that? What property makes it hole conductive or electron conductive?
Exactly. So if I would draw a molecule, you should tell me which is it, electron or hole transporting. And I guess this is possible. At least I have seen on conferences that people are saying, oh, this is a hole transporter, just by seeing the structure, and I never figured out how they do it.
Yeah, I think the answer is very complex, but probably if you know the chromophore, so that unit that strongly interacts with the light, then some experts would probably know it. I think the answer is probably in general not so straightforward.
Okay.
Typically, it's also related to the energetics. For example, B18 is a donor, but just a donor because in combination with the biceps, it would donate the electron. So this would be conducting the electrons and with the holes. But why is it like that again? I cannot really answer it.
Okay.
But if you see the band diagram, you would know, right? I mean, then you would see where the Fermi level is and whether it's closer to the conduction or to the valence band. And depending where it is, you would know if it's HTM or EPL.
That doesn't mean so much. This just means the doping. So like we have some band structure, then there's a Fermi level. This doesn't tell you so much. So yeah, in general, if you have a HOMO and a LUMO, let's say, and the Fermi level would be very close to the LUMO, then it would be full of electrons. Then it would be N-type material, and then
electron transport.
It would be likely an electron transporter, but it doesn't have to be. There are some. It doesn't have to be. I think there are some exceptions, but it's probably.
But in most cases, it is.
In most cases,
no.
Yes.
Depending where the Fermi level is, you would know what kind of a transport layer it is.
Yeah.
Because also like that, it would make the interfaces and the band alignments with the other materials.
Yes.
It's in contact with.
Yeah. Yeah, but many of those molecules, they are also ambipolar, so they can also transport both charges. Okay, I will ask Peter on that. I think he knows a better answer. Okay, now we have 10 minutes left. Are there any more questions? Okay, then we will go to a whole new chapter. for 10 minutes, which is called organic solar cells. Yeah, because so far we have only discussed the physical properties of the building blocks, which are organic semiconductors. But obviously we want to make solar cells out of these materials. Yeah. Okay. Generally, sorry. Yeah. So as other technologies, there are advantages and disadvantages. Advantages of organic semiconductors typically low temperatures, cheap, very thin, soft and flexible, and so on. You have all of this many times. Of course, disadvantages, low mobility is often unstable in air and strongly bound excitons, which creates a whole lot of problems. These are examples of organic semiconductors and organic solar cells applied. So there's one company which is called Heliotech. I think this is one of the last companies remaining. I think that's a building from them, but I'm not sure. They actually made tandem organic solar cells, and they 5 years back or so they had like 13% efficient triple junctions, and now they have not improved it anymore much, while the single junctions have now 18%. So yeah, we will see how this company goes on. And they sublime also the materials, as far as I know, and create triple junction cells with that. Anyway, here again, this example of the record single junction D18Y6. Yeah, so what is the problem for an organic solar cell in particular? We have this very strongly bound exciton, and it recombines very quickly within 1 nanosecond or less. So one possibility to dissociate, remember, 700 milli-electron volt could be the binding energy in a bad case. The room temperature is only 25 milli-electron volt. So we need a field. And yeah, so a field could, for example, separate it. High electric fields required to dissociate electron hole pair. And for some, so neat materials, so this is only, so hole only also, hole only devices, or electron only. These show a strong field dependence. Field dependence of photogeneration. So the probability to split the electron and hole depends very strongly on the electric field. You see, electric field is 1 volt per micrometer. Not sure about volt per centimeter now, but so the dissociation probability, the probability to split this exciton and take it out as free electron hole pair depends very strongly on the electric field. If you have not a bicator junction. Okay, and this was the breakthrough discovery in the 90s by Sarachivchi and Higer, actually, in 92. So they have seen that that there can be a photo-induced electron transfer from a conducting polymer to a Buckminster fullerene. So this can transfer the electron to the fullerene. This was only discovered 92 and published in Science. So they have discovered the donor acceptor mechanism with organic conjugated, with pi conjugated materials. And this was then employed to solar cells. Okay, I'm sorry, this existed already earlier. So this was a bilayer of copper tallocyanine, and this PV polyphenol. You see here, this is a bilayer, so one layer and the other. So they already know that you can make some sort of electron-hole transfer possible. But this has shown it with a C60 molecule, which is, I guess, more efficient. So that was the first organic solar cell in 1986, and it achieved the efficiency of around 1%. And this is known as a bilayer organic solar cell, so not a bulk heterojunction. We have just like two layers, the donor and the acceptor. And then this cell works like this. The donor is excited. The exciton can diffuse to the interface. The exciton splits, so the ionized donor and the acceptor, this is the excited donor, and the acceptor becomes the ionized donor and the ionized acceptor. And then hopefully electrons and holes are transported to the electrodes. Yeah, so with this you can make a solar cell, a bilayer organic solar cell, or a heterojunction organic solar cell, where the strong exciton binding energy can be split by giving this electron so much energy available to down jump to the acceptor to split it. So the offset, there needs to be an energy available for them to split. So this energy can be provided by the acceptor, which is lower in energy. And of course, so the downward jump of an electron automatically means already a huge energy loss, which cannot be taken out as an open circuit voltage. So yeah, overall, this is a terrible solar cell. And it is also terrible because remember, the diffusion length of the exciton is only 10 nanometer. So you can only make this 10 nanometer thick in this one, which of course does not absorb any light, any sufficient light. So yeah, this brings me then to the bulk heterojunction concept. So remember here, this is a neat material. Most of the charges recombine, the excitons recombine. And in the 90s or 86, they had already bilayer principles where you can only collect charges within a certain range. So only 10 nanometer of the solar cell contribute to the current. So, and finally the bulk heterojunction concept was introduced, where the donor and the acceptor is very finely mixed on a nanometer length scale. So if you excite the donor, and the mixing must be smaller than like 10 nanometer, then potentially all of the electrons can be transferred. And yeah, this was exactly the breakthrough also from Higa, actually. So DT, it seems that this is the first bulk heterojunction solar cell. It was published in 1995. Polymer photovoltaic cells enhanced efficiencies via network of internal donor acceptor heterojunction. So they employed this principle of that they discovered earlier, the photo-induced electron transfer to C60, and they employed the mixability of these polymers, and they created the first bulk heterojunction solar cell. And what properties do they specify here? So this is the need material, and this is the collection efficiency. So only 1,000th of a charge, 10 E minus, so 1 E minus 1%, only 1 over 1,000 charges are collected. And this is increased to, at short circuit, this is increased to around 50% collection in such a MEH PPB PCBM organic semiconductor blends. So there's a huge, so this is the collection efficiency. There was a huge increase in the probability to collect free charges. All right. So, of course, the morphology of this bulk heterojunction determines like the efficiency. This morphology is strongly influenced by the solvents, as shown here. You see the external quantum efficiency of such a bulk heterojunction cell. That is not so important. And yeah, so now we are done with the time for today. Yeah, this brings me now to the question how to proceed next time. I can either talk about perovskites or go more into the fundamentals of organic solar cells. You can decide. So I can either go completely perovskite next time for the last lecture, or we go more into the fundamentals of organic solar cells. Any preferences?
Perovskite.
All right. One vote.
Yes, perovskite.
All right.
Yeah.
Good. Any more votes? All right, I guess perovskite it is. Okay. Has anyone not yet evaluated the lecture? I'm sorry for bringing this up only now. I've posted a link in the group chat. So most of you have evaluated the lecture last time. I've seen there are 10 evaluations. They're anonymous. At the moment, I don't even see what was the outcome. I don't see anything. I only see that there are 10 evaluations, but I will at least write them an email to get the feedback. But so today I see here 7, 10 people, now 11 people. So at least one person has not done it. Probably. Yeah, so if you have not yet evaluated the lecture and you would like to spend 5 minutes, please evaluate the lecture just following this link. How long did it take you last time to do it properly?
10 minutes or 7. I forgot, but very quick.
Very quick. Okay, good. Yeah, so if you have not done it yet, it would be great if you can evaluate. Yeah, it's totally anonymous. If it's complete nonsense and you don't like it, you can also say that. Yeah. All right. Yeah, so thank you very much for listening, and we'll see you next time and talk about perovskites.
Thank you very much.
Thank
See
you
you.
very much.
Bye bye.
Bye-bye.
Bye.
Bye.